Okay, today we'll talk about optimization. We have been talking about a lot on calculus. We talked about the derivatives, and then we talked about the partial derivatives, and we talked about how partial derivatives are used to calculate the changes, small changes in x on the impact on y. Okay, any input and the corresponding output. Okay. We will extend the idea to optimization. Okay, so before getting into what is optimization, let's get some practical examples. Okay, every day in our life we do optimization. Okay, for our living. Okay. Suppose you want to make any decisions, you try to find the optimum decision which works for you. Okay, because we try to find evaluate the pros and cons and try to make the best which we could. Which we could afford, okay, and make a decision. Suppose, for example, if you wanted to buy, let's say, mobile phone, let's say you kind of review through online or through friends and try to find out the best phone available in the market. Okay, let's say the best phone available, the cost, let's say 100,000, or I mean, say, let's say 10,000 rupees. Okay, and that is not something which you could afford. Let's say you cannot afford 10,000 rupees to get the best phone. Then you kind of try to look into your budget. Let's say your budget is only 8,000. You try to find the best phone within the budget. Okay, and that is what you call it as a constrained optimization. So even though you're trying to find the best out of the best in the world, okay, the best in the world might probably be a little bit out of reach of your budget, so you try to find the next best which suits your budget. So you try to find what's the best I can get for the money I have. Okay, that's the optimization problem. So I mean, whatever decision we make in your life, we kind of follow the same process. Okay, even though we wanted to, I mean, it's not just in purchases, but if you wanted to make any decision on your career or your I mean education. Okay, we try to find the best possible solution for the problem, which suits all the constraints. Okay, suppose if you wanted to, I mean, study in a college. Okay, like probably the best college. Okay, probably if it is like very far from your country, which you're not willing to travel, then probably you kind of choose something good which is closer to your home or in your home country. So that is called optimization. Okay, you try to aspect for the best, but when you have some constraints, you kind of negotiate and find a solution which kind of suits you and solves your problem. Okay, so even though it is nothing, there's nothing like the best solution, but the solution that works with all the constraints. That's what is called optimization. Okay, so now let's take an example of a function. Okay, so we have been talking about a lot of functions. Okay, we'll continue to do with functions. So any problem in your life, let's say if you want to have, I mean, buy a mobile phone. Okay, you can also write it in a function. Okay, like okay, the cost of the mobile phone and the money. I mean, the budget I have. Okay, and put it into some constraints and see what it is, and try to find the best possible mobile phone for all the possible values. Okay, and try to find the best one which suits you. Similarly, we'll just take a function like this, a very simple function. Okay, it is not a mobile phone, but let's say you have x squared plus 2x plus 2. Okay, it is a function. Okay, so what this function, if you try to plot it, okay, you can use a software called Desmos. Okay, it's a very nice open source online software. You can just go there and try to plot this a function, any function, whatever I have given so far. If you try to plot it into this online application, it will start throwing you nice graphs. Okay, graphs are easier to interpret, visualize, and understand. So always I encourage, whenever you want to find what this is really looks like, try to plot it into this app called Desmos, and you'll get a function and a graph like this. Okay, something like this. So this is what this function is. So whenever this is like say 2 4 6 8, this is -2 -4 -6, and this is the graph. It looks like this. So whenever you have a optimization problem, there are two things we should look at. Okay, whether you are trying to minimize something or maximize something. Okay, when you say minimize something, as an example, if you are manufacturing some goods, Okay, and always you will try to minimize the cost. Okay, you do not want to manufacture something which is very expensive to for you to manufacture. You always try to find what is the minimum cost with which I can manufacture something. So that is an optimization problem where you're trying to find the minimum. And when you wanted to sell the product you make, you wanted to maximize the profit, which means that you do not want to sell anything in loss. You try to find out the maximum profit I can get by setting correct selling price and having the right partners, distributors, and things like that. So you kind of work with a way to kind of maximize your profits. Okay, so all optimization problems can either be used to minimize or something, or maximize something. Minimize the cost and maximize the profit. Okay, so in this case, this in this example, we are trying to find the minimum of this function. Okay, so when you say the minimum of this function, I mean it looks like a convex function. Okay, if you try to find the maximum of a function, if it's a different function like this, you can find the maximum profit I can make. Okay, in that case, you will try to find the maximum. This point is the maximum. Here in this case, this point is the minimum. So basically, you're trying to find out what is the minimum. Let's say this is a function which is used to find the cost of manufacturing something. When you're trying to find the minimum cost, I can use to manufacture using this function. Okay, so this is what it is. And so when you want to find a minimum of something, that's where the derivatives helps us actually. Derivatives helps us to find when where the slope is zero, which means that here the slope is negative. It is not zero, which means that there is some reduction in cost, but it is not the lowest cost possible. And you kind of reduce the cost, and here it is like flat, which means that slope is flat, or the slope is zero, which means that this is the minimum cost for you to manufacture something. And after that, if you try to change the values, it starts to increase, which means that the cost goes up again. So, if you're trying to find the cost of manufacturing, this point is actually the minimum cost in which you can produce some goods. So, how do you find the minimum cost? Okay, visually we have found that this is the minimum cost. Okay, somewhere around here. Let's say the solution here is like -1 in x-axis and 0 in y-axis or something. Okay, let's say this is the minimum cost. Okay, visually we're able to figure it out. Okay, now let's try to evaluate that if it is true. Okay, so what you do is you do find the derivative dy by dx. Okay, and this becomes 2x, and this becomes 2. Okay, the normal derivative. So just taking this is a constant at 0. Now, when the slope of a particular function is 0, which means that is the minimum point. Okay, so we can set it to 0 actually. 2x plus 2, we can set it to 0, which means that is the slope. Basically, this is the slope. The slope at which this function is minimum is when the slope is 0, which means it's flat to the horizon. So now if you try to solve it, x becomes -2 by 2. So x is equal to -1. So that's what we have got. Okay, so x is equal to -1 is the minimum of this function. So when you try to solve a minimum for this function, you are able to kind of set it to 0, set the equation to set the derivative to 0, and solve for x. Okay, that is how intuitively you can solve the derivative of any functions. Now life gets so complex that okay, all I mean you will not be able to get like simple functions like this where you can directly set it to 0 and try to find the derivatives. When things get so complex, okay, and we do not have an easy way to solve derivatives by just setting it to 0 and easily solving this. That is where we move into a process based empirical way to kind of solve the problem. So rather than trying to directly find a solution, we kind of start somewhere and try to find a solution. So this correlates with the example which I gave you initially. Okay, we are trying to find out 2 into what is equal to 2, is equal to 2. 3 into what is equal to, sorry, let's say 2, 4. 2 into what? 1 into what gives you 2, 2 into what gives you 4, 3 into what gives you 6. Okay, this is the function which we're trying to find in the initial example of machine learning. So we are trying to find out the value here is 2, so that it becomes, we find the multiplication tables like 1 into 2 is equal to 2, 2 into 2 is equal to 4, and 3 into 2 is equal to 6. So here we're trying to guess guess something. Okay, that's what we're trying to do now. Okay, we are trying to guess the solution somewhere, and try to find out the minimum here. That process of guessing and trying to find out the right solution is what you call it as a gradient descent. Why do you call it as gradient? Gradient is nothing but your slope. If it is a single, in this case, it's a univariate function, so it is just depends on one variable. The function is like this. Suppose if it is a multivariate function, you will find a 3D surface. Like you will not have a slope like this. You will find a kind of a 3D image of this, and it might be in two dimensions. That's why you will get partial derivatives. That's why you call it as gradient descent. So even though in this case it is not directly, we do not deal with partial derivatives here because we just have one variable. But if you have real problems, it might, you might have multiple variables, and you might have to deal with partial derivatives to kind of find a gradient. So the logical and the process is the same. So we'll start using gradient descent. Using this simple problem. Okay, so how do you go about it? We know that the analytic, the solution directly is if you substitute the derivative and set it to 0, and you will be able to get the solution directly. Suppose you wanted to do it through a process. Okay, again the random guessing process. So what we can do is we can start guessing. Okay, let's say we randomly start with the guess at x is equal to 3. Okay, let's see if x is equal to 3 is the minimum. We don't know this. We don't know that this is the point where it is minimum. And looking at this, we have the luxury of seeing this graph so that we can visually find out where the solution is. But if we don't have this graph, and if we just want the machine to find this, it does not have the luxury to directly look into something and find the solution. So it has to start some guess. Okay, so let's say x is equal to 3. What it really means is that this is the first guess. Okay, so we are trying to set and see if the first derivative, basically this, we're trying to find out if at x is equal to 3 is the slope 0. Okay, the question we are trying to ask is the slope 0 at the chosen point x? Is the slope 0 as a chosen point x? That's the question we are trying to answer. Let's see. We have chosen x is equal to 3. We know that the slope is not 0. We'll see what happens. Okay. In the first derivative, if you just substitute 2x plus 2, we are trying to find out if it is 0. Okay. Is it 0? We are trying to question mark. We are trying to find the question here. So here we substitute x is equal to 3. What happens? This becomes 3 to the 6. It becomes 8. 8 is not equal to 0. Which means that the slope at this point is equal to, at x is equal to 3, slope is equal to 8. Now let's say we know that the slope is positive, okay, which means that the slope is increasing. Okay, it's 8. Okay, so we will try to find the next guess opposite to the direction of the slope. If you choose probably x is equal to 4, you might end up going upwards. Okay, so you can even try that and see what happens. Okay, let's say x is equal to 4. Okay, let's put x is equal to 4. Okay, 2 into this is the equation you are trying to substitute and find. Okay, 2 into 4 plus 2. This is equal to 0. Is it? We are checking that. It becomes 4 2s are 8 plus 2 10. 10 is equal to 0? No. Which means that the next point, which if you choose x is equal to 4, the slope becomes 10. Which means that from 8 we have increased to 10. Which means the slope is increasing. So we know that when the slope is increasing, we cannot get to the low minimum point. Okay. Which means that assume that you are on a hill. Okay. Assume that you are on a hill. Let's say you are on a hill. Okay, and if you wanted to get down, if you're stuck here somewhere in the hill, if you wanted to get down the hill, okay, we are basically trying to find out where the slope is. Okay, if you're trying to find if the slope is positive, which means that you will be climbing up the hill. The objective is to get down the hill. You'll have to walk in the direction like this to get down the hill, right? So you need to walk in the direction where the slope is reducing. Okay, you cannot get down the hill when the slope is increasing. That's the same idea. That's why you call it as a gradient as well. So the slope is increasing here. So now this becomes 10. Okay, is the slope is 10 equal to 0? No. So this is not the point. So we started with 3, we went to 4. It's not the answer. Now let's take one step, okay, and say let x is equal to 2. Okay, let's see what happens. 2 into 2 plus 2. Is it 0? So it's like 6. 6 is equal to 0? The answer is no. But the good thing is from 10, from 8, if we increase 1, we go to 10. But from 3, if you decrease x to 2, we get the slope is equal to 6, which means that we started like this with at x is equal to 3 guess. We used 4, we found the slope is increasing, though then we reversed our decision. Okay, let's reduce 1, and we found that the slope is now 6, so it is reducing. So let's keep continuing. Let's take x is equal to 1 now. Let's take x is equal to 1 and see what happens. At x is equal to 1, this becomes 2 into 1 plus 2. 2 into 1 plus 2 is equal to 0. So this becomes 4. Okay, is 4 is equal to 0? No. So at x is equal to 2. Sorry, at x is equal to 1. This becomes 4. So which means that from 8, 6, 4, we know that okay, we are moving in the direction closer to the point which is close here. Okay, close to the lowest point. So let's move one more time. Now x is equal to 0 is not working. So let's check x is equal to x is equal to 1. So let's take x is equal to 0 now. If you put x is equal to 0, what happens? This becomes 2 into 0 plus 2 is it equal to 0? Now it becomes 2. Okay, this is 2. So the slope from 8, 6, 4 at x is equal to 0. At x is equal to 0 is here. X is equal to 0, it becomes 2. Still we have not reached the minimum point. So now let's take x is equal to minus 1. Okay, x is equal to minus 1. You substitute x is equal to minus 1 here. 2 into minus 1 plus 2 is it equal to 0? Let's check. This is minus 2 plus 2 is it equal to 0? Yes. So which means that we started off with a random guess at x is equal to 3. Then we made a wrong decision by taking x is equal to 4. We found that the slope is increasing. Then we reversed our decision. We started to reduce the value of this step from 3 to 2 to 1, and we found that at x is equal to minus 1, this is equal to the slope. This slopes become 0. That's the point here. So x is equal to minus 1. This is the minus 1 point. So now we found the solution through derivatives directly. At x is equal to minus 1, the y is equal to 0. So, but in this case, we are trying to find it through the process of gradient descent. We're randomly guessing at a particular point and trying to narrow down to a point where we can find a solution. This entire process is called gradient descent. And where do you use this? Okay, this is an optimization. Whenever there is optimization, you can use gradient descent to kind of find a solution to the problem. So in machine learning, like if you wanted to find the solution of a problem like this, okay, you can use gradient descent to start guessing and trying to find the function y is equal to 2x and where it is exactly 0 and find the value of x. So we use it in what we call it as a cost function or loss function. Okay, so both means the same. So at the end of the day, it looks something like this function. You can formulate any problem in machine learning using a cost function, and you can try to find the minimize that the cost by randomly starting with some points and try to solve. This is a very powerful method. You can try to find the solutions of any complex functions by trying to use this. Okay, and there is one more small feature here. So if you wanted to kind of, we randomly chose from, let's say 3 to, we reduced from 3, x equal to 3, then 2, then 1. We took a step or difference of 1. Suppose if you had taken a very large step, like say x equal to 3 and then x equal to minus 3 or something, we would have been jumping around here and here, you never have reached it. So always it is good to take small steps in the direction of the, opposite direction of the slope and come down. Okay, the small step is what we call it as sometimes eta learning rate. Okay, so which looks like it controls like the amount of step you take to kind of narrow down to the solution. Okay, so this is the overall picture of what you call as gradient descent, and it is used in optimization. So just to recap, we started off with a problem. Let's say this is an optimization problem, and this is a cost function. We wanted to find out the minimum cost of manufacturing something, or minimum loss of a function to find the solution to a machine learning problem. We take the derivative. We took the derivative and set the slope to 0 and find out at which point the slope is 0. That is the minimum value you need to take. And this is not possible to solve like this for all complex functions. So we used gradient descent where we started guessing random values and try to set the slope equal to 0 and fed in multiple values for x and try to find out at which values of x the slope is 0 and solve this problem. Okay. Now I'll also give you an example of how to remember this hill through a toy example. Okay. Because sometimes the cost functions will also be represented in what you call as level curves. Okay. I'll show you. I mean, it's a good way to visualize like this. You would have you would have seen this toy. Okay, so kids might have been playing with this. Okay, so what it can just it has a various shapes, and if you try to put it in the right order, you get this nice shape. Okay, so assume that this is the mountain we're talking about. This is exactly the mountain. This mountain is looking very even in the sense the slope is constant and everything looks so even. Okay, now in real world you will not have the mountain like this, but assume that you have a mountain which is like very nice slope with a nice peak. So if you try to represent each of this, and I mean look like this. Okay, you see what you call it as circles from starting with this the smallest circle to the largest circle. So the smallest circle actually represents the peak, and the largest circle actually represents the base. So if we try to if you wanted to have a 2D representation of this mountain into I mean in a paper, then you can what you can do is you can draw what you call as level curves and try to find out the slope by trying to visualize in 2 dimensions. So I'll give an example here. So let's take this. This is the hill, okay, and this is the peak. Okay, the peak has got the smallest circle, and the base has got the largest diameter of the circle. Okay, so let's take one example here. So the smallest one, okay, okay, the next smallest one, you can draw one more time. Smallest one, next smallest one. Okay, you get the idea, right? Now let me draw a little bigger, uh, bigger one. Let me put a little bigger. So, so when you what you see here is called it as what we call it as level curves, which means that when the diameter of the curve is small, which means that we are at the peak. Suppose we are trying to find the slope and try to navigate to the bottom. Okay, what we need to take care is we kind of walk through the these level curves. Okay, and try to come to the bottom of it. Okay, and the bottom probably this is the solution where we are trying to reach. Okay, we are trying to reach the base of the mountain. Okay, so we start here and we try to walk in the direction of the slope. Okay, and try to find and come here. This is what we call it as level curves. So I mean the distance between these curves tell us how steep it is. So if you see if you see here the one at the top has got the highest. I mean, here the slope is constant, so you are able to find that I mean, the difference between the level curves are even. In real world mountains, the slope will not be constant. You will find something very peak at that particular point. So in that case, what will happen is like here the slope might be low, then it might go high, then low, high. So you'll have variations in the circle in the diameter, the width between the circles. Okay. So here the slope is steep. Here the slope is steep. Okay. Then the slope is low. Here in this case, what happens is that the difference between the level curves here, if you try to correlate, will be small. And in this case, if the slope is steep, the gap will be more here. So that's how you can visualize and connect between this toy example with this level curves. Okay, and where this is used is it is used to I mean the cost function which you normally see and try to optimize, you will have a representation like this called level curves, where we kind of we try to find out. Suppose we are stuck here, we try to find the slope of the particular point near to that. Okay, and try to take steps in such a way that we walk slowly towards the least or the solution which is the minimum to this. Okay, in this here, the problem is to come down to the base of the mountain. That is the minimum point that we need to achieve. You kind of walk in the direction of the slope and then come to the point. Okay. This is an example of how you can visualize the level curves and how this is all represented in some examples out here. Okay. So we will see one more last example for constraint optimization, and then we'll close this. Yeah, we'll look into one more example for constraint optimization. Suppose you have a BMW car plant, okay, and they wanted to produce 100 cars. There is a demand for 100 cars. They have factories in two locations. Let's say one is in Chennai, India, okay, and another one is in Munich, Germany. Okay, they wanted to manufacture, let's say, two different types of cars. The first car, maybe this could be 3 series, and here they are producing 5 series. Okay, so they wanted to manufacture 100. There is a demand for 100 cars, and they have two manufacturing plant. One is in Chennai, which is they manufacture 3 series, and one we have. I mean, like in Germany, where they manufacture 5 series. And if you can represent the cost of manufacturing these two using this function, actually, the cost of producing the 3 series is X, and cost of producing 5 series is Y, and total cost of producing 3 series and 5 series is this. Okay, and the total demand of cars is 100, which means that X is the number of 3 series, Y is the number of 5 series, and the total demand is 100 cars. Okay, so they have the total demand of 100 cars. So they wanted to find out how many should I manufacture in each of this plant in the least I mean like possible cost, and try to meet the demand x plus y is equal to 100. So that's the problem. So when you say cost function or loss function, this is what it means actually. So we're trying to find the minimum cost of this, and trying to find out the with the constraint. So when you have, what is the constraint here? The constraint is you can manufacture, the demand is only 100 cars. Okay, so we need to manufacture 100 cars, and we need to find a minimum cost for this. Now let's try to solve this. Okay, so x plus y is equal to 100, which means the total demand for 3 series and 5 series is 100. This is a constraint, and this is the equation. Now whenever there is a function, and if you wanted to apply a constraint of it, okay, you can write it using what you call it as a function of lambda, which is called Lagrange multiplier. Whenever there is a constraint, you can use this method actually. So what does it say is 3x squared plus 6y squared, okay, minus lambda of x plus y minus 100. Okay, we are trying to find out the optimal cost for manufacturing this I mean two cars. Okay, x is 3 series, y is 5 series. Okay, and the cost of this manufacturing of this is given here, and we are trying to find it with the constraint of x plus y is equal to 100. So you can write it, you can bring the 100 here, and you can try to make the equation like this, x plus y minus 100. Okay, and this is a constraint. So this constraint you can try to find it. So we are trying to find the minimum of this function. Okay, minimize the cost for setting this here. Now the earlier gradient descent, I used just derivatives. Here we need to use partial derivatives because it has two variables x and y. So partial derivative can be written as dy f1 by 2x, or the other way is you can write as a subscript like this f of x. This is also a partial derivative. If it is like second partial derivative, like second order partial derivative, you can use two x's here, which means that it's basically df1 by dx, just notation. Okay, so now let's take the partial derivative of this function with respect to x, then y, then lambda, and set it all to 0 and find out what is the minimum cost. So let's do it. Okay, the function with respect to x. So if you do it with respect to x, this becomes 6x. This becomes a complex. Expand this actually before we try to even take the partial derivative. Let's expand this function, which is equal to 3x square plus 6y square minus lambda x minus lambda y minus lambda 100, and just multiplying lambda inside. So this is the function we are trying to find the minimum of. So we'll again take function with respect to x, which is also denoted as f subscript x. It becomes 6x. This becomes a constant 0. So this becomes minus lambda. This is again a constant 0. Again, this is a constant because we don't have x term here. This is partial derivative with respect to x. Similarly, we can do a partial derivative of this function with respect to y. Okay. So this becomes 0. So this becomes 12. Okay, 6 is 12. 12y square. So 12y. Okay. And then minus this becomes 0 and becomes minus lambda. Okay. So next is partial derivative of this function with respect to lambda. So this is a constant 0, this is a constant 0, this becomes minus lambda, sorry, minus x, minus y, minus 100, minus x, minus y, minus 100. So that is the equation of all the partial derivatives. Now let's see what happens if we all set the partial derivative to 0. So here it becomes, if we set this to 0, this becomes lambda is equal to 6, 6x. Okay, this goes here lambda. Okay, x is equal to lambda by 6. This is what x means. Then y equal to it becomes if you also set this to 0, y is equal to this goes here. Y becomes lambda by 12. And here okay, now if you substitute this x and y in this equation, it becomes minus lambda by 6 minus lambda by 12 minus 100 is equal to 0. Basically, what you are trying to say is you can just just rearranging the value for the value of x, value of y, and you have three partial derivatives. Okay, the one with respect to x, the one with respect to y, and one with respect to lambda. And you're trying to substitute the x and y in the third partial derivative, where you can try to get the value of lambda if you substitute x and y. So it is like minus x minus y minus 100 is equal to 0. So lambda by 6 minus lambda by 12 minus 100 is equal to 0. If you take 100 to the other side, it becomes, and if you try to find the common denominator, it becomes 12. And if you multiply, it becomes minus 2 lambda minus lambda is equal to 100. So here it becomes minus 3 lambda by 12 is equal to 100. Okay, which becomes 3 by you can minus 100 actually. So this minus and minus gets cancelled, and lambda is equal to 400. So we obtained the value lambda is equal to 400. So that is the value of lambda. So if you try to substitute the value of lambda is equal to 400 in any of this equation, here you might get x is equal to 400 by 6. So x is equal to, it's approximately 6.6 or something. So we can make it 67. And here y is equal to 400 by 12. It will be around 33 or something. Okay. So we get, you need to manufacture 67 3 series cars, 33 5 series cars to get the at the minimum to get the minimum cost and get the maximum benefits. So that's what you mean by constraint optimization. We are trying to find the value of x and y with this constraint x plus y is equal to 0, where the cost is minimum. Now if you try to find out the value of this cost, let's say when x is equal, we found that it is 67 cars and, of 3 series, and 33 cars of 5 series. So this is the minimum. If you try to substitute this into this equation, you will get the minimum cost. Okay, and try to find it. If suppose if you try to change the values. Let's say we manufacture 68 cars and of X series, and just reduce one here and make 32 cars here. Okay, then what happens is the cost will not be minimum; it will change. So if you want to validate it, okay, what you can do is you can substitute Yeah, we'll complete this by giving a couple of examples of if you increase the cars by one, or if you decrease the cars by one, what happens actually. So this is the original numbers, 67 3 series and 33 5 series. If you put it into the cost function, 67 into 33, this is the cost you get. Okay, some 20,000 or something dollars or so, whatever it is. Okay, and if you try to decrease the car of 3 series by one, and increase the car of 5 series P1, and if you see the cost increases, so which is not the minimum. If you also try to find like try to increase the cost car of 3 series by 1, and try to decrease the 3 series 5 series by 1, okay, these are different x and y values. If you try to give any number of x and y values, it will not reduce the cost from below this actually. That's the reason it is called as the minimum, and that's what we call it when we have arrived at this. Okay, this is an example of a cost optimization problem. I think one small correction here. This should be minus into minus is plus actually, and this is plus, and this is plus. So, I mean, I have taken care of the minus here, but actually here it is plus. Okay, so yeah, this is an example. So there are a couple of more optimization or regularization techniques like L1, L2. Okay, when we talk about linear regression and things like that in future, probably we'll discuss about that. Okay, so this is the overall basics of optimization. Okay, thank you.